Previous class, actually, we give you we introduce you what is the electron migration, which means actually is you apply the electrical field on your materials, and that would and the generated electrons flow have chance to push the atomic flux. This is we call the electron migration. But this phenomenon is not always happen, only happen on the current density of electrons flow density is very low. Then we can observe this phenomenon happen in our materials. And based on different material systems, actually, we talk about we classify into two cases. The first one is we have ionic materials with interstitial charge ions, and the second one is we have it is a metal materials but with the interstitial atom inside. So how to quantitatively is to describe the atomic flux of these interstitials in our interesting material will be explained and will be introduced in following slides. And as you know, if our material system belongs to ionic materials, then we have a dilute dopant positive copper ion in our materials when we apply the electrical field. When the current density is very high, which means the electrons flow is very large, then these interstitials atom positive ion have chance to be pushed toward to the anode. So the relative atomic flux can be expressed like this. If there exists a concentration variation, then we got this term. And if there's definitely there's the second driving force is the electrical field. So we got the atomic flux driven by the electrons flow. And this is the flux of interstitial, right? And due to there are two possible driving forces, so you also can write down the current density part equals to always obey the Ohm's law. So as long as you got the atomic flux and the current density, so you already can well describe the phenomena, the diffusion process in these materials. But some people actually have more interesting on the conductivity of this kind of doped ionic material. The reason for this is they want to use this kind of doped ionic material as a solid electrolyte in battery. So they want to increase the conductivity of the doped ionic material. However, they have no idea how to increase the conductivity. So we find some interesting stuff between the atomic flux and current density in this ionic material. In most of cases, ionic material have poor electrical conductivity due to they have a very strong ionic bond, right? So who contribute the current density in this type of zinc sulfate ionic material would be this the flux of this interstitial actually is a positive copper ion. So there's a relationship between this, right? So current density can be expressed like the charge of this copper ion and times the atomic flux. And if we further assume that there's no concentration variation of this copper ion along these materials, so we only have these terms contribute from the electrons flow. So we directly times the Q1 to this one and we got this relationship. So now we know the electrical conductivity of this doped ionic material can be determined or can be improved by diffusivity, concentration, and the charge number or charge state of this interstitial. So this is why we try to expand this more. Okay. So next, when we switch the material system to the metals, and first material system we want to address that also is the we also have the dilute dope interstitial in our metal materials. So because there's two driving forces, first one is possible would be the chemical potential gradient, and the second one would be the electrical field we apply on the system. So you also can directly write down the current density and atomic flux. And as we mentioned, we are more interested in the atomic flux part, right? So in this part, we want to can be expressed by like this because we have two possible driving forces, right? And the first one is obey fixed first law, so you use the minus diffusivity concentration gradient, and the second driving force acting on the atom, these interstitials, belongs to electrons flow. So we use the mobility concentration and driving force to represent it. The driving force part, as we mentioned, will be expressed like the beta E. Beta is the effective charge. So it is some mention of both these forces acting on these interstitials, including the electrical field effect and also the electrons flow effect. Okay, so now we can directly write down the atomic flux equals to the concentration variation parts and also the electrons flow. The electrons flow serving a driving force acting on these interstitials. And if you want to simplify these conditions, you can make more assumptions. For example, like we also assume the concentration variation of this interstitial. We don't have any concentration variation, means the concentration of this interstitial is uniform along these materials. So what we have here is atomic flux all contribute from the electrons flow. So as you know here, the value for beta, we need to measure that. So we also introduce you how to measure or determine the value of beta. For experimental design, first of all, you need to have a metal and you dope some dopants inside and allow the concentration of this dopant are uniform along these materials. Then I'm going to apply the electrical field toward to left-handed side. So that will result a current passing through the left-handed side. So which implies that your electron flow will go to the opposite direction, right? It's go to the right-handed side. So you are going to, this electron flow is going to push the atoms moved from left-handed side toward to right-handed side. So you are going to have this kind of profile of this interstitial. And this is an atomic flux driven by the electron flow. But as you know, as long as there are concentration variation presented in your materials, so the fixed first law, the concentration gradient part is going to counterbalance the effect, the flux driven by the electron flow, right? So as long as both these flux reach the net flux equals to 0, then we can get the beta, the value for the beta. But some people question about what means the Quincy steady state. That means doing your measurement, for example, like one day, probably your experiments will spend like one day. Then when I measure the concentration profile of this interstitial on like 12 hours after, and then I also measure that 24 hours after, then I found that the concentration profile did not change a lot. Then under this situation, I can assume now the system already reached the Quincy steady state. Because the definition for steady state means the time should be like reach, should be very long, right? But during our experiment, we cannot wait until like several hours or several years or something, right? So we assume that kind of a measured time period is the quincy steady state. Okay, so under this situation, as long as the temperature you know, the concentration profile, you just take the average of the the average of the concentration of these interstitials and also the concentration gradient, you can get that from the EPMA, right? And also you know the current density and also the electrical conductivity. So you can determine the value of effective charge beta in your own systems. So this is how we measure the beta. So let's move the other case. Now what we have here is we have pure metals, which means the atoms located at the substitutional site or lattice point. And under this material system, then we also apply the electrical field on it. So what's the atomic flux of these substitutional atoms? So because we only have two components, right? The one is the atoms at substitutional site, or you can say that at the lattice point. And the other component will be the vacancy. So based on this, you know the diffusion occurs when these atoms exchange the location with the surrounding vacancies. So this is how these atoms diffuse through these materials. Okay, so you have this idea. Then, as we know, we apply electrical field on these materials. And we have a relationship between the JA plus JV will be equals to 0. The net flux will be equals to 0. So when the atoms move toward to left-hand side, then that also means the vacancy will move to right-hand side. So we got a JA plus JV equals to 0. So in order to know the atomic flux, one way is directly measure the atomic flux, right? And the other method probably would be if I can measure the vacancy flux, then I also can have chance to know the atomic flux. The difference just the sign. The value should be the same, but the sign will be different, right? So for the first method, is that easy to directly measure the atomic flux of these atoms? It's not that easy. Why? Because we only have, this is pure metal, right? So in order to get the JA, you need to know the mobility of the A atom. Concentration of the A atom is easy. You can know the concentration of atom A, right? And the driving force. Driving force probably you will use the beta E to substitute that. But the question here will be, it's very difficult to measure the mobility of the atom A without labeling the atom. So here it's not easy to directly measure the JA. So in this way, we try to perform the other approach by measuring the vacancy flux. So now the vacancy flux actually comes from two different parts. The first one is due to the concentration gradient or chemical potential gradient, and the other vacancy flux will be come from probably because the electrical field we apply on these materials. So in order to, so probably some people will, in the meantime, will write down like the J flux can be expressed like the first term is due to the concentration or chemical potential gradient, and the second term is due to the electrical field we apply on the system. And regarding to the chemical potential gradient part, you know, the mu A chemical potential of atom A can express like this. And in these systems, this is XA, right? And in these systems, because we know the numbers of atoms much larger than the NV, right? So you can delete this term and you got the log 1. So here we got the mu A equals to mu A0. So in this case, we know the chemical potential gradient actually equals to 0. So based on this, we have some idea that the vacancy flux is contribute from the electrical field or electrical potential we apply on these materials. And the other idea is why? Yes, based on calculation, we know that there's no chemical potential gradient of A10A. And the other meanings or the other reasons to explain chemical potential of A10A equals to 0 can be considered that in our systems actually this term equals to 0, it means this term equals to 0, right? And there's no concentration gradient of the vacancy. The reason for this is the vacancy actually we don't have real vacancy flux because vacancies are easily trapped into the crystal imperfection side. So that means we got a vacancy sink, which actually like the crystal imperfection side, for example, like the edge dislocation, grain boundary, and so on. So the vacancy concentration actually is uniform everywhere. So from this point of view, we don't have this term. So based on this, we know the vacancy flux actually direct or contribute only from the electrical current. So based on this, we got the JA equals to minus JV, and JV only contribute from the electrical field part. So you can use the E. E actually here means the electrical field be applied on these materials. So we can rewrote this term as a mobility concentration and driving force. Mobility of vacancy, concentration of vacancy, and the driving force acting on this vacancy. So mobility can be expressed like this. Is the diffusivity of vacancy divided by KT. Because it's vacancy, so it's easy to measure that to get the diffusivity of vacancy by SPM or STM. As long as we have some material analysis tool to visualize the vacancy, so we can get the mobility of vacancy. Concentration of vacancy is the same idea, right? As long as you can visualize, then you can estimate the concentration of this CV. And the driving force here is expressed like the beta E. And the beta here is not the effective charge here we talk about actually is the vacancy. So we use the vacancy to point out this effective charge actually we talk about is a vacancy. Okay, so based on this idea, this is a vacancy. So in most of cases, the effective charge for the metal usually would be negative, which implies that the atoms moving the same direction with the electrons, right? And when we talk about the vacancy, the effective of vacancy usually will be the upside sign of the atoms we just talked about. So in most of cases, they will be positive. Positive means what? The vacancy will move the same direction with the current. Okay. So let's give you a quick summary for electron migration. So if we observe the electron migration happen in our materials, so we need to modify the atomic flux of the atoms, no matter it's at the interstitial side or substitutional side. So first of all, you need to determine what kind of material system you are dealing with. If we have a dope materials and the dopants were located at interstitial sites, then the atomic flux of this interstitial can be expressed, can be separated into two terms. The first term is due to the concentration variation of the interstitials, and the second term is due to the mobility, concentration, and driving force is due to the electrical field performed or applied on these materials. And if we don't have, actually, the material system, we switch to pure metals, and this the diffusion mechanism is the vacancy mediated mechanism. In this case, because it's pure metals, so we don't have any chance to plot the concentration profile as a function of time in that case. So the only way we can get the atomic flux of these substitution atoms is by calculating or measuring the vacancy flux. So it'll be expressed like a mobility, concentration, and driving force. And this driving force actually is, we use the beta VE to substitute this term, okay? So as long as you have electron migration happen in your material system, you need to modify the force. The acting force is the beta E. Beta is effective charge. In this case, it's effective charge of atoms, and this is effective charge of the vacancy. And the sign of effective charge actually tell you the direction of the moving atoms or moving vacancies. Okay, it's either alone if it is negative, so means the same direction with the electrons. If positive, that means this vacancy is moving the same direction with the current. So now we move to some examples. There are two examples usually happens in semiconductor industry. It's not a good. Actually, there are two effects we call the Bleach Effect and current crowding. Both these effects actually will decrease the reliability of the microchip. So we want to avoid this effect. In order to avoid this effect, we need to know what are the Bleach effect and what are the current crowding. Then we have chance to solve it, to avoid this effect, right? Okay, so this is a whole story. So first of all, we want to talk about, so what is the Bleach effect? Some people call it as a short stripe effect. Based on the definition, there is no electron migration damage when the length of the conducting line or interconnect is below a critical value, which means when the line or interconnect below a certain value, then you are not going to observe EM damages, which means the void formation and the extrusions. So let's take this as an example. What we have here is we have a silicon dioxide substrate. On the top of it, we deposit or grow a molybdenum line, and on the top of it, we deposit the aluminum line. So as you know, and we also apply the electrical field, and anode is here, cathode is here. And we know the resistivity of the molybdenum is larger than alumina, which means alumina have a higher conductivity. Based on this, we can observe the electrons flow is from where? Is from the cathode through a molybdenum line, and will go up and go through the alumina line and back to the molybdenum line. It will go this directions, right? As long as this electrons flow is high enough to have to create electron migration, then what? This electrons flow is going to push the alumina atoms to go this way, right? And that means there's in the beginning it's vacancy, but vacancy will grow, will accumulated growth form the void, and void will get larger and larger. So if this situation continues, then we are going to observe the EM damages, including void formation and the extrusion of the alumina atoms. Okay, so some people probably will ask, are there any, but sorry. So based on this idea, when the line above or below critical line length, then you are not going to observe this void formation and extrusion. Does that imply or tell you that there's other driving force to try to counterbalance this EM damages? Yes. So this is what we call a stress field of these materials. Due to what? Due to there's more atoms accumulate at the anode side and left more vacancies here. So locally, if you take a look on this region, you can observe there's a compressive region. And this is a tensile region compared with the compressive region. So there's a stress field. This stress field is going to induce atomic flux, try to counterbalance this atomic flux driven by the electron migration. Okay, so I'm going to, in order to quantitatively measure the effect, how large this atomic flux is. But before that, we are going to show you some pictures related to the extrusion. So this is we call a heel lock and void formation in wire, and what we have is we have a wire, right? And but you can observe there's extrusion here and void formation here. So that will result the void will get larger and larger, then the probably will lead the open of this circle, right? And sometimes extrusion. You also will observe the other types of extrusion is a whiskers. You can observe these whiskers. And the other extrusion and void formation will be like this. We have a substrate and we deposit metal 1 and insulator and metal 2 layer by layer. But when it happens, some extrusion that will lead the short circuit happen between metal 1 and metal 2. And the other, if there's a void formation here, that will lead, and the void get larger and larger, then that will lead to the open circle. So this is what we want to avoid, right? We want to avoid the extrusion and void formation on all the interconnect, all the while we are synthesis or in our materials or in our device. So how to quantitatively estimate the critical length? Which means when the line is smaller than the critical length, then what's the critical length? As long as we know the critical length, we can design the interconnect or conducting line to the length for this conducting line to below this critical line to avoid the extrusion and for your formation, right? So how to estimate this critical delta x, the length? So based on this slide, we're going to show you how to estimate. But here, what we have is we have green metal 1 and deposited metal 2 in orange. And you can observe when the length of the interconnect get longer and longer, and the void formation and the extrusion will get worse and worse. So when it's below or shorter than the critical length LC, then we don't have chance to observe the EM damages. So this is important, right? So how to calculate or estimate this LC? So in order to that, we need to formulate the atomic flux. The first one is come from where? It's come from EM, right? Electron migration expressed like a mobility, concentration, and driving force. And that's the other driving force, which we call a stress field, acting on these materials to counterbalance this EM effect. This atomic flux driven by EM. So this is also can express like what? It's a mobility, concentration, and the driving force. So the mobility concentration part, I believe you guys are okay to this. But what's the driving force here? This is stress field, right? So the driving force can be can be written as what? You take the gradient on the work, so it's a minus work. Take the gradient on it. So here the work is, you can use the stress times the volume, then it will become the work. The unit will become the work. Is, for example, like stress is the force applied on the unit area, we call it stress, right? You times the volume, so you got the force times the distance, so it's the work. And take the gradient respect with a distance x, so you got the driving force. So some people will call it as, if you take a look here, this is a stress gradient. So some people call it a gradient of back stress. So this is the atomic flux driven by the stress field, and this is driven by the electrical field we apply on the systems. As long as the value they reach the steady state, means the Ja equals to 0, then you can have a equation like expressed like this. So after arrangement, we put the current density Je and length means the length delta x here, and put the critical here, then put the other parameters here. So we got this relationship, right? As long as you determine what kind of material you are going to use for this interconnect, then you can measure you definitely know the electrical conductivity, average atomic volume, and also effective charge. You can measure this by like previous slide, right? The one we just mentioned in EM, how to determine the effective charge one. But here delta sigma. What's a delta sigma? Sigma actually is a stress. So what's the stress here? You need to put in what kind of material property related to the stress, this stress. I would suggest you use this is a stress versus a strain. I would suggest you to use the yield strength to substitute this term. The reason for this is when the stress is smaller than yield strength, this material will be the elastic behavior, right? But if the stress is larger than yield stress, there's a deformation form, right? The deformation of this material happen, right? So this is a reason why I suggest use the yield stress to substitute this term. So now we know, as long as, and for the current density part, as long as you know this interconnect is responsible for which microchips, then you already for sure know the driving current density. So under this case, you can directly get the delta x is LC. What's the maximum length or critical length for this for this materials or interconnect? Under this case, for example, like probably would be like 200 micrometer. So for the IC design, I will always design the length of the interconnector connector shorter than 200 micrometer. For example, it's like this. So this is we call the Bleach Effect, short strap effect. You need to calculate or estimate the critical length of your interconnect or your materials. Then next would be the secondary effect of the electron migration. People call it is a current crowding effect. So what this means? What we have here is we have a substrate. We grow the nitride, titanium nitride on the top of it, and also have an aluminum line. And when we apply the electrical field, then you can observe the the electrons passing through the nitride, then go up to the alumina, then move forward, then go down to the nitride part. And if you check the current density, definitely there's a stress field here in homogeneous stress, right? Because the electrons definitely will accumulate here, and this density will be very large. So when you run the simulation of current density, you can observe this region, the current density is quite high, right? But however, this region is quite low, lower by like 3 orders. And we know lots of electrons, the electrons flow will go to the right-hand side. That will result in lots of atoms accumulate at this region, and that probably will lead to the extrusion, right? In the meantime, the vacancy will be accumulate at the near here region, right? But actually, there are 2 directions for these vacancies. The primary vacancy flux will toward to this region. I believe you guys all know. So you can observe the void formation at the cathode. But actually, there are secondary vacancy flux toward to along the the gradient of the current density. Here we call it secondary vacancy flux. The reason here is you can consider this go left is a current, right? Current is going to passing through here, and when the current meets the vacancy, that it will kick. You want to move the vacancy away, right? Why? Because the current always go to the path with shortest resistivity. So you want to push the vacancy out to reduce the resistivity of the path, the electrical path in these materials. So in these reasons, some of the vacancy will be pushed toward to the region with lower current density. So the direction will be the gradient of the current density toward to this way. So we sometimes will observe some void form in the low current density region. So let's take an example here. If you move back to this slide, page 25, the direction of the electrons actually is from here to go to the left-handed side, right? The majority electrons flow go this path, but however, and you can also observe some void form here, right? It's okay, but you can take a look. There's a big void form at this region, and based on these figures, you know this region definitely for sure is a low current density region, but we'll still observe some void form here. So this is evidence showing that the current cloudy effect also will lead the void form.